flat plane is a fixed point of the soft barycentric refinement map. It's a unique fixed point in 2 dimensions. In higher dimensions there are no fixed points. In 1 dimensions there is also the one-dimensional lattice or cyclic graphs. But the 2-dimensional case is really exciting because the density of states is now interesting. So that's what I was trying to compute this week, to get an explicit formula for the density of states, which is the law of the soft barycentric limit. It's like the central limit theorem in probability theory, where you get the Gaussian distribution. Here, when we look at 2-dimensional graphs, we let the renormalization map run. What we get is we get to a limit, a unique limit, which it's like in probability theory converges in law. There's this eigenvalue form a discrete measure, and weakly this converges to a unique fixed point, and in this case it is explicitly given because we have that hexagonal lattice, and it's something which has been studied by condensed matter physicists for a very long time, especially Van Hoof. And so typically what you see in the density of states, you see singularities. And so this is called the Van Hoof singularity. In 3 dimensions it would have 2 peaks, but it's related here just to the critical points of the diagonalized matrix, right? This matrix is operator. This is a bounded operator on a Hilbert space, and this Fourier theory gets you the Fourier transform, and the Fourier transform is explicitly diagonal. It's a multiplication with a function. But it's not like in the the lattice, the usual lattice. When you have the square lattice, there you have 2 independent random variables. Somehow you can look at the tools of probability theory like characteristic functions to get to the density of states as a convolution. But in this case this doesn't work because the third direction which you have here is depending on the others. So this reflects here. So these are independent random variables because they are different perpendicular, but here this is correlated. So it's not clear what the density of states is. So I spent some time really. First of all, you can compute that. That's not the problem. That's a calculus question. We can do that in 21a. We can get this area, compute this area. Not explicitly, this is not possible. These are transcendental functions, but you can at least try to kind of then see what this function is. So here, until the critical point, there's another critical point of this function. So there's minima, there's maxima, there's saddle points. This is a saddle point. Critical values are 8, maximum is 9, the 0 is like for Laplacians, always is the lowest point. And what happens is I try to fit this with known functions. So far I could not find anything which fits, and also here. So that would be kind of an interesting thing to get an explicit formula for this density of states. So far I've not succeeded, but there is one thing which I mentioned last time. I mentioned a piecewise linear function. That was actually the potential. So this measure on the interval 0, 9 is absolutely continuous measure, and that's the density of that. That's the law of the probability distribution. And what happens is that if you look at the potential theoretic, so if you charge the interval with that density, what happens is the potential on that interval is piecewise linear, which is really interesting and which gives hope that, I know that from parts of number theory where the same kind of problems appear, where you have piecewise linear thing, and then you have to look at the Hilbert transform. So maybe there is a formula for this, explicit formula for this density of states. But that's it for today.